What are the biggest secrets of space? Till now the biggest secret of space is dark matter. We know that dark matter and dark energy make the 85% of our universe. But the mystery is that we do not know exactly what dark matter is. Scientists are researching dark matter until now they haven't found any clue. What is dark matter? Nobody knows for sure. However, we do have some clues as to its makeup. Here's a summary of what we do know. The earliest evidence that dark matter existed came when astronomer Vera Rubin refined a technique to determine the rotation velocities of stars within spiral galaxies. After she and her team accounted for all of the visible material within galaxies, dust, gas, stars, it turned out that the stars in the outer portions of galaxies were rotating at much higher velocities than would be expected. In this image of a galaxy, the upper line consists of the measured velocities of stars within the galaxy. Notice how they move faster and faster as one moves away from the bright inner, and presumably massive, inner core of the galaxy. The lower line represents the velocities that would be expected were visible matter the only thing acting gravitationally. We would expect that, as the hypothetical stars get further away from the massive center of the galaxy, they would move more slowly. But they don't. There was, it seems, something else there. That something had mass but didn't show up in any surveys from across the electromagnetic spectrum. This whatever it is was given the name dark matter. So, this tells us the first thing we know about it: it exists. What is it, though? Is it invisible particles, similar to neutrinos, that don't interact with the rest of the universe electromagnetically, thus producing light? A hypothesis known as modified Newtonian dynamics, MOND. In an attempt to answer this question, astronomers have devised detectors and have taken images of galaxy clusters to observe how dark matter, particle or MOND, works. Gravity, according to general relativity, is the warping of space. As such, a massive object will tend to bend light around it like a lens. Astronomers can image very massive galaxy clusters and look at the warping effect they have on the light coming from distant galaxies beyond. This effect is known as gravitational lensing. In this Hubble Space Telescope image of a massive galaxy cluster, the thin arc-shaped bands of light are the warped images of galaxies in the far distance beyond the galaxy cluster. By measuring the amount of warping, astronomers can determine the mass of the cluster. By imaging the cluster, astronomers can determine how much normal matter there is. It turns out that this, and just about every other, galaxy cluster is a great deal more massive than can be accounted for just by looking at how many stars and how much gas and dust there is in this cluster. In fact, the visible matter is a very small portion of the overall mass observed via gravitational lensing. This leads us to the second thing we know about dark matter: it's more common than normal matter. As surveys of such massive clusters were undertaken, astronomers began to be able to work out, using gravitational lensing, the distribution of dark matter. It turns out that astronomers can not only figure out how much bending there is, but they can also work out, more or less, where the dark matter is in the cluster, in much the same way that one can determine the shape of a blob of glass by looking at the way it bends light. One noted study compared the apparent distribution of dark matter, from lensing to the distribution of hot hydrogen between the galaxies. Hot hydrogen permeates intergalactic space and has a certain amount of mass on its own. The question was, would dark matter follow more or less the same rules as normal matter? Here's one result. This is an image of a pair of galaxy clusters that come out of a long, slow-motion collision. On this image are superimposed two colored blobs. The red blob is the measured distribution of intergalactic hydrogen. The blue blobs show evidence of where the dark matter is via gravitational lensing. This is worked out by subtracting the effect from the visible normal matter. The stunning thing is that dark matter does not seem to have the same distribution as normal matter. Moreover, it behaves differently. While the hydrogen is left behind somewhat after the collision, in other words, the hydrogen collides with itself and slows down while the denser, less diffuse stellar matter moves on its merry way, the dark matter distribution seems to follow the average distribution of the cluster. This tells us the third thing we know about dark matter: it doesn't interact with regular matter or itself, very much, except gravitationally. Moreover, it acts hot, that is fast-moving, in that it doesn't clump up much on small scales, but it is not relativistically hot in that it is moving at a significant percentage of the speed of light. Surveys of galaxies have allowed us to determine that the amount of dark matter doesn't always seem to have very much to do with the amount of normal matter in a galaxy. In many cases, for instance, small, low-luminosity, dwarf galaxies have a great deal more dark matter relative to their apparent amount of normal matter than much larger galaxies. This tells us the fourth thing we know: dark matter is probably not the result of some weird trick that gravity is playing at massive distances. But that's still a remote possibility. Finally, scientists have attempted, using various techniques, to detect the interaction of dark matter with normal matter in much the same way that neutrinos, particles that only very grudgingly interact with normal matter, it is said that a neutrino can pass through a light year of lead without a collision, were detected. Here is the interior of a device using one such technique. Is a massive tank of ultra-pure water. Astronomers look for evidence of dark matter by looking for light flashes given off when particles collide with the fluid.